Okay, today we're going to see an example with a unity feedback loop, and let's try to look at an example here with the transfer function. What we have in here is this is your system here, where you have a unity feedback system with a transfer function, and the feedback is 1. So let's take a transfer function something like this, as g of s is going to be equal to, here we put k times s squared plus 2, and then you have this one that have s plus 3, and then we have s plus 4. Okay, so now let me disappear from here. We're gonna go and look and concentrate on building this transfer function in MATLAB. And we're gonna build the transfer function in MATLAB and get the root locus plots. So that's what the question is. So let's just go over here, and then here's where we have MATLAB. We need to have both windows together. So let me see if we can do that. The other window is this one from here. No, it's this one here. Let's do the same thing for this one. Okay. Okay, so here we have the MATLAB. What I would do is this. The first thing is I need to define this variable s as if it's a transfer function type. So any operation that I do with it, it becomes a transfer function. That is a little trick that is very useful in MATLAB. So I would do this so that you say, okay, s is equal to the transfer function of, in this case, s like that. And when you do that, the computer, MATLAB knows that this variable is 4 transfer functions. It makes it just easier to enter here. K is the value of the gain that the root locus plot is going to change from 0 to infinity. In other words, we want to test all k. That's what the root locus means. Okay? So in this case, you're going to say that the numerator of this transfer function is, you would say the numerator is equal to, we need to enter it as a as you see it in there, because right now if you put s to the, let's say s like this, yeah, plus 2, yeah, and then you close the parentheses, that is the, oh, I made a mistake. X2 is what we need in here, is s squared plus 2. That's what it means. So now so that's the numerator. You could, the denominator, you could define it as, again, like these factors. I like this form because it's easier to enter, like this, and you say this is multiplied by s plus 4, like that, yeah. And once you do that, you could just say that your transfer function g is the numerator divided by the denominator, because you see all those are transfer function type. And once you have done that, the MATLAB is working and understands that g is also a transfer function. Because let me show you a different way of entering this, because I want to empower you with as many tools as possible. So I'm going to repeat the procedure, but entering it a little different way to see if we end up with the same transfer function. So I would call it G1, and I would just say, listen, G1 is S square plus 2, like that. And then you say this is going to be divided by, and I like to be very specific with the parentheses in there so that everything is very well understood. You are dividing by the product of those two, not by the first one. So if you do it this way, doing it the parentheses, it is very helpful and it's very clear. If I click return, it better be the same transfer function. And see here, let me just go here. There it is, both of them are the same. So you have a couple of options to enter. The author of your book, he gives you a third option. He uses that CONV command, which stands for combination, to make the products of these polynomials, or the products of each one of these factors. I find it easier to do it this way. But I encourage you to do it this way, but feel free, whatever works easier for you. At this point, once you have the transfer function in there, and you see what has happened is we had it like this, and the numerator is of course expressed here, but the denominator is already expressed as a product in here. So if you go to MATLAB now in here and type, you just say our locus of this transfer function of g, then you will obtain the plot. See right there. So this is the way this would be. So you can see that the these are your poles, and you have the 0 at 2. So 0 minus 2. Is that right? This one? No, here's what happens. This is how you need to read this. S squared is equal to, with 2 or minus 2, you're gonna get the poles in there, Yeah, in the imaginary axis. But this one is plus or minus the square root of 2, so that is 1.42. That's what you see here, see? 1.42 something. That's are these points. This belong to the numerator. But these two guys belong to the denominator. Those are the poles, the ones that you see with the X. So when k is equal to 0, or you're not going to get anything here, but k is equal to 1. If k is equal to 1, these are the points right there. This, that's where k is equal to 0. See, of course, that's exactly what I did. And I encourage you to do that, you know. Huh? Yes, it does. I say, look in here. The gain. The gain. Yeah. So, so what happens is that the roots of the characteristic equation, they begin at the poles, but they end up at the zeros when the value is very, very high for the gain. This is why if you click over here, the value of k, see what it says, infinity in there? But if you were to click over here, what is the value of that? You know, the gain is 0 point something, you know. That's how you see the root locus of this transfer function. So now why don't well, any questions about this? Okay, so now what we'll do is one request was to be able to put the feedback that would not be 1. If the feedback is not 1, you know, what would it be? Okay, so if this is not 1 anymore, then let's just propose something. Let's propose that we do a unity feedback system, not unity feedback, but what we will have is this situation. We'll have a situation where this is g of s, and then we need g of s. We are going to put a feedback which we call it h of s. Okay. And when we are doing the root locus plot, I think it's important that we draw the block diagram correctly so that you realize exactly what's happening here when you are doing this kind of a design. Let me erase this lining here. Small eraser. Okay, a small eraser. That's good. Let's just erase this line. Okay. What you're doing is you are entering a controller here that has a value of k, and the inventor of this root locus plot, Professor Evans, that's what his theory was, that you should be able to use this k to predict whether the system is stable or not. And you are going to make the plot of all the roots of the numerator and the denominator of the transfer function of this closed loop system, changing k from 0 to infinity. So basically it's the design of a proportional control. That's what it is. This is your reference, and this of course is your output on the other side. Okay, so I think we need to propose some change in the transfer function. We could, okay, so this is g of s, yeah? And then I am going to add this h of s. So h of s, in fact, is another transfer function. So we could propose one simple transfer function to see how it does together with the one we already had. So in here we could say this is maybe, you could say this is one like another factor like s plus 5, something like that. And so this block corresponds to this block right here. Okay? So how do we do this? I think at this point it is important to establish the fact on a unity feedback system. How is the closed loop transfer function when you have this kind of thing? So if this is no longer 1, but what we are saying is that this is h, then this is h of s in here. If you have this feedback loop in here, you can say, and maybe I'll just change colors in here so that we do a little bit more emphasis on this. Isn't it true that in this place in here is the error, right? And here you have that the signal in here that you have is like the error of s is the reference minus c of s multiplied by h, right? Is that right? See? In other words, this error in here that we have, the error that we have is this minus this. And this signal here is c times h. So r of s minus c of s. But the other one on the forward loop, you know that c of s is equal to the error times g of s. See? Okay. So if you use this and you put the in other words, we eliminate the error from here, then we will find a relationship that we have that would allow us to find this relationship between C and R. So what I would do is from this equation, I would say C of S is equal to R of S minus C of S times H of S, yeah, and this whole thing multiplied by G, right? I just replaced it. All right. What I'm trying to do is to find out an expression for the closed loop transfer function when h is present. That's what I am trying to do. So we'll continue with that from this expression that I have in here. From this expression that I have in here. I will just multiply this. Just say C of S is equal to R times G of S minus C of S times H times G. Okay, so what you want to do is to move the terms to the other side. I'll continue down here. You have C of S, and then you will put plus. Move it to the other side. You have C of S, H of S times G of S, and this is equal to the reference times G of S, like that. So let's continue here. You have the output. C of S is equal, it's equal. Bad boy, I need to erase that. That is over here. And then we say this is 1 plus G of S times H of S, like this. And this is equal to R of S. So you see, now it becomes clear what we have to do to obtain an expression where we have the transfer function that we want. See, in here you have the transfer function where you say C of S, which is the output, divided by the input, in this case R of S. Isn't it true this is going to be G of S divided by 1 plus G of S times H of S. So when you have a closed loop system like you see here, when you have it like this, where you have the feedback in here, the closed loop transfer function, once you have entered that H of S, is going to be what you see in here. It's going to be C of S over the input is G of S over 1 plus GH. Okay, so having, seeing this, then you have to first create this in the numerator, then create this other one in the denominator. Yeah. Now remember what we did in the previous example? We entered this into MATLAB. So I don't think that you probably don't want to see it repeated, but this is already defined. What we don't have is this H. So can we go on from there? Does anybody have any questions about that? In other words, we define this G now. Yeah, we define this G, but that is already in our MATLAB entrance that we did. So let's just, here we go. So just to make sure we're on the same page, G, this is the transfer function for G. But now we need the other one for h. And then a new transfer function that will define, see, in other words, h is 1 over s plus 5. So what I would do is I go in here into this part right here. And so you have this one, you will say, why not, I'll just say h is equal to 1 over parentheses, remember? See, once you have defined that this, it really becomes easy to do it this way. That's why I encourage you to, first define the variable, the Laplace variable s first, and then define this transfer function. So I am going to define it as g2. This is going to be on the numerator is going to be g, right? I would say g, and then divided by, what do we have? 1 plus g multiplied by h. See? How is that? Is there everybody? See? The new transfer function is what I have on the left hand side over here. What I have on this side over here. What I have in here is g over 1 plus gh. That's what I need. So click on return. I'll make sure that we are on the right hand side here. There we go. No, I didn't do it right. We need to be over here. Yeah, there we go. Of course, I put two stars. We only need one. This is your new transfer function. New transfer function became complex. Take a look. This is the transfer function that we have now. G2. We'll see. I just put a random one. I don't know let me just, this is my new transfer function. Okay. I may or may not have done something right to the system itself, but I mean, the reason that I have a little bit of a question is because the numerator has the same polynomial order as the denominator, but we'll see what happens. Our locus, and then we have, this would be G2, and then we'll see. Well, okay, this is, didn't go crazy, but I think it became a very unusual root locus plot. What you have in here is you have in here the imaginary axis, and this is the real axis. You see you have 5 roots and basically 5 zeros. So 1, 2, 3. See there you have 3 roots here, 3 roots here and 2 here. And you have the zeros 1, 2, 3, 4, 5. So this is how the system would behave, the new closed loop system. And so this is your new root locus plot. So the message that is important here is to realize that when you do that, your transfer function changes. Your transfer function has to be this. Yeah. is g over 1 plus gh, which is very common and you should remember that. But in this case, you ended up with a totally different root locus plot. All right.